I'm a cloud engineer from professional services located in Amsterdam, Netherlands. And today I will talk about Hive Metastore. We have a product called Data Metastore, which is a managed Hive Metastore service. It uses MySQL in the backend, and we you're trying to move it to Cloud Spanner. It's not released yet, but we already in contact with the community, Hive community. We're trying to push our changes. Today, I would like to talk about the challenges that we face so that you can learn about how to move from MySQL Cloud Spanner. I will also explain you what Hive Metastore it is. It's also, I think it's a good learning. And yeah, there will be some parts, boring parts about details, but let's see how it goes. So first of all, let's start from file format versus table format. What does it mean? So think about it. At the bottom, we have a data lake storage, Google Cloud Storage, S3, HDFS. On top of that, we put our data in different formats, CSV, Alvaro, Parquet, based on what we want. But on top of that, still we need a table format where we organize these files in such a way so that these data lake engines, Spark, Hive, they can access the data fast. What does it mean? So in the right side here, you see table format from Hive. Basically, it's a partition. With this one, you don't have to read all the data in cloud storage. Instead, in your SQL query, when you run the query, you're able to prune some of the locations. So you can only read data belongs to 5 p.m. immediately without reading all the Parquet files in your data warehouse. So, but where is the data to begin with? We know there's a structure of the data, okay, but where is that data? How many tables inside? And that comes from the Hive Metastore. It tracks the databases. What are the databases in my data warehouse? In which GCS bucket? Tables. How many tables I have? What is their name, creation type? What is the file format stored in these tables? Partitions of the tables, really important. Columns, compactions, which is related to transactions, transaction tables, which Hive supports ACID transactions. The idea is that when you do insert and delete at the same time, only one of them wins. And for this, for organization of that, we need transaction tables. Let me show you briefly what is inside. Just a second. Yeah. So this is a Spanner Spanner. Inside Spanner, we have a Hive Metastore, and all these tables you see in here, they belong to Hive Metastore. For instance, like databases table. Here you go and see the data. As you see here, we show that this database name, it is stored in this GCS location. It is owned by normal user, something like that. Or if we go to, I think tables should be another page. Yeah. So for instance, a table, what is stored is in here as well. And you see creation time of the table, which database does it belong, access time, name, etc., and some other information. All these are stored in Hive Metastore, and which means that whenever you make a Hive query or Spark query, first it goes to Hive Metastore and reads all the information, all the data that it needs to continue processing the data. How important it is? Well, basically, many of the tools that you use, open source tools especially, they somehow depend on the Hive Metastore. And new table formats, Iceberg, Delta Lake, these they don't have dependency, direct dependency on Metastore. They can but still use it to uh, as a side Metastore location. So therefore it's really central location in the whole open source ecosystem of data warehousing. How it works? Uh, we have on the left there are engines, Spark, Presto, Hive. They use Thrift protocol to access the Hive Metastore service, and this service is a stateless service. We can put as much as Hive Metastore service. It's basically Java code. You can put in a container and run it in parallel, scale out easily. But the bottleneck here is the relational database storage. If your relational database cannot handle this load, then basically your Metastore queries fail, etc. So here the biggest challenge in here is the relational database store. Currently, in our Dataproc Metastore managed service, we use MySQL, and it is behind the Cloud SQL, which normal customers you don't see it, but in the backend it's how it works. But then we're considering now Cloud Spanner. Why we consider Cloud Spanner? Since Cloud Spanner is a distributed database, it scales horizontally. Other databases like MySQL, you can create read replicas, but writes should be from the master node. So you cannot scale out the master node easily. You can do sharding to add more master nodes, but it makes the whole architecture complicated. Instead, Spanner, it has all the relational semantics, schemas, asset transactions there. You can write SQL. It has a JDBC connection. It is a Hibernate, ORM, it supports, etc. And on top of that, it scales horizontally. It's really high SLA. It's fully managed. More to go into detail, Cloud SQL, which is the MySQL main service that we offer, is currently it is 99.95. It is SLA, and for Spanner it is 4 nines regional and 5 nines multi-regional. So really, we provide higher availability. And as I said earlier, Metastore is a central place. So every query that you make in Hive, Spark, it goes first Metastore. So availability of the Metastore defines your system's availability as well. Location, Cloud SQL is a regional resource, but Spanner can be regional and multi-regional. For instance, you store your data in Google Cloud Storage. It can be multi-regional, and you think that, okay, my data is multi-regional available. It's good, but when you want to query them, if one of the region goes down, and if you have a problem there, then Metastore cannot give you the metadata, and you cannot query your data. So it's really good to have a multi-regional database in the backend. Maintenance window. Cloud SQL has a maintenance window, since you need to upgrade the MySQL versions, for instance. You need security patches in the OS in the backend. For these ones, you have to define a maintenance windows, which decreases the availability of the service. But for Spanner, there is no maintenance window. You don't see it. Access control. Cloud SQL is based on this normal MySQL, so user credentials all the way. Recently, we add IAM support too, but still user credentials is the default one. And you need network connection for it, Cloud SQL, which means that like you need to open firewalls, etc., etc. But Spanner, it is IAM native, so it provides GCP IAM by default, and it's API based. So this part, if you use Dataproc Metastore service, you don't see it at all. But in the backend, it makes our life easier to make something IAM native and API based. So these are the motivation for us to go to Spanner from Cloud SQL. So what needs to be done for this to happen. Uh, Metastore service is this blue square here. Think about this, as I said, it's a container, and our Metastore APIs, Java, written in Java, and a treat API accessing to this. They access to these databases by using in two ways. One is there's a Data Nucleus, ORM. It implements JDO, Java Data Store, data objects, I think, standard, and it creates tables, etc. Some mutations are done on Data Nucleus. But for performance, Hive community created directly SQL calls to JDB over JDBC connection, like joins that are well created for the performance. And so what we need to do first, we had to add support for Spanner to Data Nucleus, and then we need to update these SQL queries. So how to integrate with Data Nucleus? We need to match SQL types to Spanner. It's kind of easy since Spanner doesn't have so many types. For instance, all character related types goes to string, float double goes to float, numeric to numeric. It was pretty easy. SQL syntax to Spanner, it was kind of easy as well. So we need to deal with the format. For instance, how to add a limit keyword. Many databases work a little bit different, and we just applied those. Not a big deal. But sometimes we hit some blocks that Spanner does not support fundamentally, so which we cannot do much. For instance, there is a information schema of Spanner table where you can query what tables inside Spanner, and Data Nucleus uses this table. There are some internal Data Nucleus tables that it uses to organize its objects, and for those it uses them in a read-write transaction Data Nucleus. However, Spanner does not allow this. What we did, these Data Nucleus tables that should exist in Hive, luckily Hive was already creating them in advance. Data Nucleus does not have to check them, so we simply skip that check in Data Nucleus. We patched it. This was by chance, we were able to avoid that, but in the end there are some Spanner features, fundamental features that you may hit on the road. For those who watched recently Google Cloud Next, we had a new offering, Postgresql Interface for Spanner. When we saw that, we thought that maybe we don't have to change Data Nucleus at all, since it already supports Postgresql, and there's an interface in front of Spanner which really allows us, okay, there's an interface Postgresql Spanner, the backend is backend Spanner, in the end Postgresql in front, so we can just use existing Data Nucleus. Unfortunately, it's not that straightforward. In the end, if a feature of PostgreSQL, if it is not supported by Spanner, then it's basically no-go. And so it's really important to understand this interface allows you to write PostgreSQL, but in the end, you're still bound with the Spanner features. And some of them may not be. Some of the PostgreSQL features cannot be done with Spanner. And just the previous example of information schema, using PostgreSQL interface doesn't make a difference. So we decided to keep changing Data Nucleus. What we dealt with the Hive integration challenges, some of them are like there's in Spanner you can do a mutation in one single transaction, 20K mutations, and mutations are inserts, deletes, etc. And number of mutations is number of rows times number of columns. It's not just rows, columns as well. The partitions table inside Metastore. I think it has 8 or so columns, which means that if the number of partitions of a table, data warehouse table, if it's more than 2K, then Spanner was giving errors. Luckily, this also exists in other relational databases. So Hive already have a feature for that. You need to load partitions, operate on partitions in parallel. Uh, that's one of the challenges of Spanner. Cascade deletion when you have a foreign key relations is not supported in Spanner directly with foreign key. The only way to support them is, for the time being, by using subtables, which is we call in Spanner interleaves. What that means is that you have a table and it is a foreign key relation with another table. You can embed the other one, the second table underneath the other, and they appear in the same location in the disk, so that it is easier to read them faster. And when you delete, cascade deletion is possible. So we had to change a few tables for their schema. Some other challenges, JDBC does not support some features. There was wrong use of parentheses, etc. We have to change the SQL basically. The reason I'm telling is that these are the kind of changes we had. We changed the schema to fix the cascade deletion. We changed the SQL statements to deal with the mismatches. Some good surprises, at least I didn't know when I started, is Spanner provides native session pools, so you don't need a connection pool. That makes things easier. And there were some fundamental problems like this one. So select for update is a feature that many relational databases support, and it's not supported yet in Spanner. Select for update is a blocking operation. You're telling the database, I'm selecting these rows and columns. If anyone else try to read them before I commit my changes, block them. They don't allow them to read. And Metastore uses this to create transaction IDs. Transactions IDs should be monotonically increasing 1, 2, 3, 4, 5, so that we know the order of operations happening on the data warehouse. Spanner does not allow two operations create the same transaction ID, okay, since it is a serializable level isolation, but it doesn't block reading them, which means that two processes at the same time try to create the same transaction ID. One of them wins, the other one fails. But in the original MySQL case, the other one just waits for it. So now, basically, the failing one should retry. Luckily, retry operation was already in Hive, so we didn't have to do anything. It's just, I think when they created the Hive Metastore, they already realized that retry should be a part of it, so it's only retried. And Spanner has a feature, as a hint basically, where you can provide in your select statement like this, lock scanned ranges exclusive lock, which is basically select for update operation, but it is a hint, so it's not guaranteed. Spanner tries to do that basically in the backend. And these solutions made us deal with such fundamental problems as well. What about the performance? First of all, we don't expect Spanner to manage MySQL. The reason is that Hive Metastore schema is not designed for Spanner. If you know other distributed databases like HBase, Cassandra, when you work with them, you will realize that they have primary keys. In fact, they even call this partition key, which means that they want you to distribute the data to many distributed nodes as much as possible, so that the operations can happen in parallel. You don't overload the same node. Spanner is the same. It is distributed, which means that if you have sequential IDs in your primary keys, it will end up in the same location, and some operations will get slower. And this is the case for Hive Metastore schema. And we don't want to make really drastic changes on Hive Metastore schema. Another one is foreign key relationships. Think about that. In Spanner, tables can be in different nodes. And if you join them with foreign key relationships, it may not as performant as having them in the same machine. Some foreign key relationships, we cannot make them interleaved due to the schema. Otherwise, if we make them interleaved, they will appear in the same locations so that our queries will be better. Secondary indexes, there are lots of indexes used in Hive Metastore in the backend. So, for instance, DB ID is primary key, but DB name has the secondary index on it. The existing schema of MySQL, you just put a index on the column, just the DB name, for instance. But in the Spanner, you also need to add other columns that you need to read with the secondary index. You may think about the secondary index as a new table, basically, so that you need to add all other columns that are supposed to be read. So this requires schema changes again. You cannot, so it's not simply copy the MySQL schema and push it to Spanner. So you need to adapt this as much as possible. And fortunately, Hive Metastore operations take only a tiny fraction of the overall data warehouse query time. You make a data warehouse query, it's not normal OLTP database. You don't expect milliseconds. When you make a data warehouse query, mostly you said, okay, in a few seconds, tens of seconds, minutes, even hours, I will get my results. And Hive Metastore operations take really a fraction of this, and maybe a few seconds, less than a second mostly, which means that lower Spanner performance does not mean that the overall effect is negligible. So this is really a good consideration for you if you thinking about moving MySQL to Spanner. You should think about, should I change all the schema, make really drastic changes to go to Spanner, or am I fine with just a little bit performance degradation? Summary: we were able to remove MySQL, replace with Spanner, and we had some challenges. Schema not designed for Spanner, bad performance. There are some lack of SQL, JDBC features. We had to find workarounds. Data Nucleus, another open source tool we had to patch in order to use with Hive Metastore. But what we get in the end, higher availability, for nice regional. Our product is not multi-regional yet, but now it will be easier to design a system for multi-regional. In the end, Spanner can be multi-regional. We don't need maintenance windows for version upgrades or OS patches, and it's also good for the customers. They don't have to think about what should be the maintenance window. It's not there. And we have cloud native access control with IAM, which is good for the backend, where it makes our operations easier, basically. And that's it.